Hi everybody, we are pleased to present our paper in WCAS 2020 edition, a solution for designer verification of a parametrizable interleaver and the interleaver for visible light communication. It's been developed by the master and undergrad students Matheus Silva, Gabriel Araújo, and Elisa Bacelar, and advised by the Professor Ricardo Duarte at Universidade Federal de Minas Gerais. Enjoy the presentation. Our research group is currently designing a file layer for IEEE 802.15.7, which is a standard that regulates short-range optical wireless communications. One of the blocks required by this file layer is the interleaver. Its main goal is to mitigate bus errors that are very harmful for error correction code methods, in this case, a Reed-Solomon codec. We couldn't find any available open source implementation that fits our project. Then we will decide to implement an open, reliable, and parameterizable IP core for an interleaver, compliant with VLC standard, but also applicable to other contexts due to its flexibility. In order to illustrate the usage and impact of the interleaver in communication systems, we will present the transmission process of a frame in a VLC system with and without interleaving. Some encoding and decoding steps are abstracted in this explanation. Each block in the diagram represents a symbol, and a group of blocks of the same color represent a code word. In this case, the frame corresponds to three code words: yellow, blue, and green. So we will start with VLC without interleaving. Firstly, the input code word is treated by the Reed-Solomon encoder, which is responsible for including redundant symbols to the data. Those symbols are represented by the boxes with darker color. The yellow code word leaves the RS encoder with 5 symbols and is transmitted to the communications channel, while the next code word enters inside the RS encoder. When data reaches the receiver, it enters inside the Reed-Solomon decoder and is recovered in order to obtain the original message. Now we will illustrate the occurrence of a bus error, which results in 3 erroneous symbols within the blue code word. The RS decoder is unable to recover the erroneous symbols because they violate its maximum capacity of error correction. Therefore, the information carried in the blue code word will be lost. In the end, we can see that due to a bus error, we are only able to transmit correctly 2 out of the 3 code words of the same frame. Now the process will be repeated for VLC system with interleaving. As the code word leaves the RS encoder, it is written column-wise inside the interleaver block. And then it starts to send data by reading symbols in a row-wise fashion. The mixed symbols are sent through the communication channel. And as they reach the receiver, they are stored inside the interleaver, which is responsible for unscrambling the data. During the transmission, a bus error occurs, which results in 3 error symbols. The interleaver waits for all symbols to be written. And then all the frame is written, the code words are sent in their original order to the RS decoder. The number of erroneous symbols in the yellow code word is within the Reed-Solomon correction capacity, and thus the original message can be recovered. The same happens to the next code words. And in the end, all code words are recovered and the frame is received correctly. So that's why interleaver's usage is so important, not only to VLC, but to many other communication standards. And providing an open implementation of a generic interleaver can be helpful to many people working on communication systems. Besides VLC, DVB and WiMAX also use interleavers. They are the standards that are mostly found in technical papers about the subject. In addition, Altera, Xilinx, and Let's also provide interleaver IPs for general purpose use. Those commercial IPs are the works that most resemble our project. Since our goal is to provide an open IP, it is interesting to have a documentation of its interface and parameters. The parameters that can be set during the IP instantiation are the maximum number of elements stored in the RAM, the fixed number of lines, the symbol length in bits, and the mode, that is, if the IP will function as an interleaver or an deinterleaver. So, here you can see a figure that illustrates the interface of the IP. For inputs, we have clock and reset pins, I start code word that indicates the start of a frame, I end code word that indicates its end, I valid that informs the validity of input data, I data, which is the serial input data port, and I consume, which is a signal that indicates that the block which consumes the output data is ready to receive all data. For the outputs, we have O in ready, which indicates that our block is ready to receive new input symbols, O start code word, O end code word, and O valid, which work in the same way as their input counterpart. O data, which is the output serial data port, and finally, or error, which indicates an error status of the system. Now we're going to cover the architectural aspects of our proposed RTL design for performing interleaver and deinterleaver functions. Our IP is basically constituted of 5 main blocks: the controller, which keeps track of the state of the block; the address generator, which is responsible for indexing memory locations to be written and read according to the permutation rule specified by the block interleaver function; the write and read status selector, which determines whether the block is receiving or transmitting a code word; the flag signal generator, which informs to the control unit the start and end delimiters of the input frame and also if the number of input data symbols exceeded RAM capacity; and finally the RAM, which stores the input frame. It's worth to mention that the only difference between interleaver and deinterleaver is the memory addressing mechanism. For the interleaver, as the maximum number of lines is known, and the interleaver process follows column-wise direction during frame reception, it is possible to use a 2D memory to index rows and columns independently. This approach reduces the complexity of the address generator, since it demands only simple increment operations. On the other hand, as the interleaver requires row-wise direction during frame reception and the total numbers of columns is not known beforehand, then 2D run does not help at all. For that case, it was used a linear run, and the address generator is responsible for calculating the index hops to implement the interleaver function. The next slides illustrate the main states of our IP based on a typical waveform. Whenever the reset pin is asserted, the block goes to the wait for symbol state. That defines that the data path is in writing mode. When a valid symbol is detected together with a start code word signal, the next state becomes receive. It means that O_n signal is enabled, and then the address generator increments its outputs accordingly. If an input happens to be invalid, stall will be reached, freezing the data path and disabling the run writing. If not, the RAN will continue to be filled until the end of the code word delimiter is asserted. When it is the case, the controller goes to the last input state. During this state, the data path transitions from writing to reading mode, and the address generator saves the state of its outputs and resets them to 0. The first output cycle is informed to the controller by the flag signals generator. Afterwards, it moves to consuming state. That means that output data is available, and it remains unchanged until a consume signal is received. Whenever that happens, the controller asserts O_n, and the output indexers are incremented accordingly, column-wise for the interleaver and row-wise for the interleaver. RAN indexes are incremented until the end of the code word delimiter is reached, which is informed by the flag signal generator. Finally, the IP returns to the wait state, and the process starts over again. The error state may be reached whenever the RAN exceeds its maximum capacity. If iValid is enabled when Interleaver is in the transmission mode, or if iEnd code word is set without any previous iStart code word. In order to certify the correctness of our IP, a verification task has been carried out. It focuses on the IEEE 802.15.7 parametric values. We used a formal approach to verify the IP. It uses tools that mathematically analyze the state space of the device under test instead of performing a traditional simulation based on input vectors. The system requirements to be verified are expressed in system verilog assertion properties, and the formal verification tool informs whether a property is proven or has a counterexample to debug. The formal verification tool adopted in this work is Cadence Jasper Gold 2019-12 version, and this is the machine used to run the experiments. Our verification methodology has 3 steps: reset and interface control, interleaver functional check, and interleaver plus the interleaver functional check. Reset and interface control aims to check if control outputs are working as expected. 16 checks were created for that, and they are proven easily in less than 10 minutes. The next step is to verify the functional aspects of the interleaver, which means that the address generator must calculate the memory indexes accordingly. 11 checks were created for that. Some checks could not be proven for the original memory size. Then, memory was reduced to 50, and this value was increased progressively until 200, and full proofs were obtained for these scenarios. The whole process took 12 hours. Then, the functional aspects of the interleaver is verified using the interleaver itself, which was already verified. They are connected together, then we could create a simple property to check it using the assumption that input data of the interleaver and output data of the interleaver must be equal. We could not get a full proof for the original memory size, so we had to scale down the memory size by 10x to get a full proof in 14 hours. Some FPGA synthesis results are collected for our IP instantiated using the parametric values specified in IEEE 802.15.7. A device from Altera Cyclone 5 was selected for such analysis. Resource utilization is dominated by the RAN, and other components use less than 150 logic and register elements. The maximum frequency is 84 MHz for the interleaver and 134 MHz for the deinterleaver. It's lower for the interleaver because the synthesis tool did not synthesize a 2D run, and the linear run with a 2D to linear convert logic was instantiated instead. This additional logic, which is the critical path, was responsible for decreasing the maximum frequency. The critical path of the interleaver is shorter and only has a few combinational gates on it. These results suffice IEEE 802.15.7 throughput requirements and are comparable to results extracted from other commercial IPs. However, Fmax reported by the IP version provided by Xilinx is considerably higher, but such comparison is not accurate since different tools and devices are used to report the results. We can summarize some takeaways from this work. We could end up with an IP which is parameterizable, simple, and available for the community. It also meets the requirements established by IEEE 802.15.7. Formal verification could be used to attest the correctness of the IP, and synthesis results are comparable to commercial IPs. For future works, we would like to explore memory abstraction to increase proof convergence in formal verification, and to investigate the 2D run synthesis issue, and also to implement new features to the IP, such as inter-row and inter-column mechanisms. The authors thank CNPq, PRQP-UFMG, CAPS, and FAPEMIG for the support, and also Cadence Design Systems for providing license. Thanks for watching this presentation and feel free to ask any question.